So now we're going to have Jennie Pryce is going to join us again, and Jennie and her collaborators have spent a little bit of time actually taking us back through what's happened in DairyBio, and so this is a really important section of having a look at what we've got to look forward to between 2021 and 2026. And just as an audience, I can actually guarantee you silence is golden, because that's respectful for the speakers, so I appreciate that. Thanks. So I'll invite Jennie. I don't need to introduce you to the group, so I'll hand over to you to take us through the next 5 years. Thank you.
Thank you, Graham, and I have the unenviable task of being between you and your drinks. I do have a few disclaimers as well because of the time of day, and the first is that we may have some unintended entertainment. We have a singer in our household, and she's got quite dubious taste in, well, what she thinks are Aussie classics, and the definition of an Aussie classic for a 4-year-old is this. Look it up, Teeny Tiny Stevies, and that's what she loves singing. That will probably be a good outcome. More likely is that she'll mimic the cat. That's our pet cat there. Now, we're going to be talking this afternoon about DairyBio 21 to 26, a glimpse to the future. I'll try and go at a reasonable pace so that we do get through this quite quickly. You've already seen this graph heaps of times, so I'm not going to explain it again. All I want to say is how we're going to take this to the next level. Genomic selection has undoubtedly done us a tremendous service in terms of rates of genetic gain. We've seen some of the downsides. Let's think about where we might go into the future. So what will be the next game changer? I think it's probably going to be how we use this tremendous amount of data that everybody has very nicely introduced today. So I think that the next game changer is going to be the way that we combine next generation genomics with all of these high-tech phenotypes that we've been talking about today. So there are lots of disruptive technologies that are going to help us with this next quantum leap forward. Next generation genomics, such as long-read sequencing that Iona generously introduced, sensors that we also heard about earlier today for new phenotypes like heat tolerance, fertility, lameness. These molecular biomarkers, Heather actually did a job of introducing that, and I'll give you some examples. And this kind of multi-omics approach of basically bringing together all of that information in a way that we can use. Now, this is quite a big task, and we've already heard the challenges, especially when we think about implementation, drawing together all of this sort of information. But the whole thinking behind where we're going next is to try bringing together more of this information in a way that we can develop next generation breeding values and even performance indicators. So using MIR, genomics, new ways of measuring phenotypes, sensor data, and having better definitions of these traits. This is it in a nutshell. We're really well set up for the challenge. We have, I think, an enviable situation when overseas researchers look at the way that we as an industry are organized. We have research heard that it gives us deep phenotyping and helps us with validation experiments. It helps us with high resolution traits that we can't possibly generate in large scale without other options, which enables to get larger numbers of animals, but perhaps on more focused phenotypes. So, for example, if we think about Ginfo Elite being those farms that can provide us with sensor data, molecular phenotypes, and bringing together data in tens of thousands, that will certainly help us Going down the next tier, the broader GINFO population with health, fertility, helping us with the validation of some of the tools that we generate above. And always having genomics and genotype data as being the thing that ties all of these three tiers together. Let's go down to the next tier, and this is where we have commercial farm data. But there is a huge opportunity here. We had Feng talking earlier on about how we can have mid-infrared spectral data and phenotypes on potentially millions of cows using traditional farm records. As long as they're herd testing, we have the MIR data. It's really a huge opportunity. Let's think now of some of the challenges. Now, obviously, we've got things like farming in a difficult environment that's warming, dealing with climate change, and having that social license to operate. Now, not only are we working, I suppose, in the animal area, but we're future-proofing the types of forages that we'll be breeding as well. So the DairyBio forage program is focused on demonstrating the DairyBio technologies, delivery of new technologies, and development of future forages. With the PhDs really in that disruptive space. So these are the real big groundbreaking areas. It's very similar for the animal program, and obviously that's what I'll be focusing on today. But we're thinking primarily about two main platforms, if you like. One is all the things that fit under long-lasting cows from birth to maturity, with an emphasis on lifetime profitability. And the second is adapting to a changing environment and maintaining diversity. So what we just heard in the previous panel discussion. Now, the studentships, again, focused very much on those disruptive technologies, the really risky things. And I'll give you an example of one of those shortly. All of this research is funded by Dairy Australia, the State Government of Victoria, and the Gardner Foundation. And we're incredibly fortunate to have this kind of structure that funds this sort of research. It's really fantastic to have 5 years of research bundled up to be able to deliver some of these prospects. Now, it is currently under consideration by these organizations, and actually this is very a fortunate occasion to get you to think about how this might benefit your organization, your farm, and also have a chance to input into the process. So let's talk about what's in store for herd improvement. And let's take the survival story first. So first of all, why is it important? Well, I hope it's almost a no-brainer. It puts you into the driving seat of when to make replacement decisions. The great thing about survival is it is a multifactorial trait, that it captures different aspects of health and fertility, and quite often the traits that we don't already have breeding values for. So, for example, you might think that we don't have a breeding value for lameness, so that's currently soaked up in the survival breeding value. It's also, not surprisingly, the second biggest driver of profitability after protein yield. And it also has an important role in reducing per cow emissions. And I'll come to that in my next slide. It is a hard trait to evaluate because it's late in life, and it's also what we think is very likely to be sensitive to genotype by environment interactions. So let's talk a little bit about methane. Now, the rumen contains a very large microbial community, and this is often referred to as the rumen microbiome. Now, in the fermentation process that occurs in the rumen, energy is manufactured, and there is a byproduct of that, which is methane emissions. But in breeding for more productive and more efficient cows, we've actually reduced the emissions on a per litre basis. So we already have a good news story in terms of our emissions of per unit of product. And this has been shown in several studies. This is an Australian one showing how we've driven that down through selection and also feeding. But of course, that's not really enough in terms of where the targets are at. There's already an agreement in place that Australia has signed up to, which is reducing our emissions by 26 to 28% of 2005 levels by 2030. Now, this relies on tackling the three major greenhouse gases: carbon dioxide, methane, and nitrous oxide. Now, for the dairy sector, 57% of the emissions are methane. So that's obviously where we're putting most of our focus, and that's why you'll hear methane as being the main trait that we'll look at. In addition to this, it's a key strategy for both the Victorian government and Dairy Australia. So it's obvious that this has to take a priority role in research projects going forward. Now, the work that we've done does suggest that there are some more good news stories in terms of other breeding values that have a favourable effect on emissions, notably survival and feed saved, because of course breeding for more efficient animals that last longer reduces the emissions. So if you have fewer replacements, then you obviously have less emissions for your entire herd that includes the followers. So one area that is worth, and what we're currently looking at, is that we think that based on these, I suppose, data-based observations, that HWI, or the health weighted index, may have better environmental impact credentials than the BPI. But that's something that we'll explore and quantify more accurately. What we need to be able to do this research is accurately measured methane data, and we're very fortunate that the Ellenbank team, particularly Peter Mote, have really been very much world leaders in developing a way that we can measure individual cow methane emissions at pasture using this type of wearable equipment. So this is, I suppose, a very high-tech sensor that every time a cow breathes out, you can measure the concentration of methane in her breath. And it's been checked in individual chambers for data quality. So it's very high quality data. We've put quite a few batches of cows through this equipment, and we've currently got individual methane emissions for 480 individual cows. We also have feed intake data. We also have milk yield data. We also know something about their ruminal fluid, fecal, milk, and blood sampling for their microbiome. And Boris, who's in the audience with you, he's doing his PhD to try and understand the role of the microbiome in that sense. Shaylee Richardson, who is a PhD student also with me, but based right now in Canada, home country of Canada, her project is really bringing together those pieces that we've already identified as being the big winners so far. So longevity and feed safe breeding values, bringing that together with methane data and potentially overseas data to think about whether we can develop prototype methane or greenhouse gas breeding values for our dairy industry. Now, of course, we're not going to stop there. We think there's plenty of scope in bringing that multi-omic approach to this sort of trait. We could also bring in other, I suppose, predictors that we think may be useful. So in this sense, information from the rumen microbiome that Boris is working on, information from, say, MIR or key metabolites that might be useful, may also contribute, in addition to potentially other polluters. So that gives you a little bit of a flavour of where we're heading in the methane area, in the methane space. Now, let's talk a little bit about heat tolerance. I suppose this is another breeding value that we are very well known for in Australia. And right now, the breeding value is based simply on the reduction in yield that we see as cows get into a more or a hotter and more humid environment. And we think that there's plenty of opportunities to bring this new thinking to improve heat tolerance breeding values. So in addition to that yield reduction, we think there's plenty of scope for using MIR, potentially metabolomics. We think that individual genes that tell us, or genetic variants to be more precise, that tell us something about the biology of the trait will also play a role. We also think that sensor data will play an important role here. And in addition to where we have it, core body temperature. So sensor devices, we've already heard about this today, but basically sensor devices can tell us all sorts of things about potential new phenotypes. Now, I guess the ones that are of specific interest to potentially heat tolerance are respiration rate, and potentially even lying behaviour as well. These are things that we need to explore in terms of the role and the importance of helping out with these new sort of breeding values. What we have done recently is to have a look and see if we can find individual genetic variants that help us with our prediction of heat tolerance. And this is the work of Evans Chariot, who's looked to see if using a very big genome-wide association study, if there are variants that might help us with genomic prediction. Now, his data set is big data plus. He's working with 29,000 cows that have 15 million imputed genotypes. So these are predominantly cows from Jinfo that we have imputed the sequence data, and Iona explained how that was done. And we've brought this together with milk and weather data, and it gives us some pretty powerful signals that help us with genomic prediction. And Evans is currently doing some validation to see how valuable these genetic variants are in improving our heat tolerance breeding value. And of course, it relies on this very important repository of bull or cattle genomes. So Iona talked about this. I won't cover it in any detail through the interest of time. What I did want to mention, though, was some of the exciting work that we've been doing with international collaborators as well on validating our heat tolerance breeding value in a completely different environment. So this is work from the University of Florida. What they did was sent DataGene, the genotypes for several thousand cows from a Californian dairy herd. And then Laura and her co-worker here, Liz, went and measured the core body temperature of cows in pretty much the hottest time of the year in California. It's when the wildfires were happening, so it was also very smoggy. And pretty much the first week into it, they both came down with COVID as well. So they certainly deserve a medal for their achievement, in addition to the quality of data that they've produced. They showed that cows with high heat tolerance Australian breeding values have lower body temperatures under heat stress in US conditions. It's really powerful stuff. In fact, the work was very similar to the controlled experiment that we had running at Allenbank, where we put cows in individual climate-controlled chambers and showed that, again, there was a difference in their core body temperature. The body temperature difference between the two lines is actually quite similar in the two studies, so for Laura's and also this study published by our colleagues at Allenbank. Now, we heard Heather White talk this morning about metabolic health and the importance of that. Obviously, most disease happens soon after calving, and it's important because that we want to set up the cow for lactation. So improving transition cow health has both positive impacts for cow longevity, fertility, and animal welfare. Now, for a few years now, I've been working with Tim Luke, who was originally a vet from Gippsland, in addition to Simone Rochford, who is a biochemist who works in our group and has all of this amazing, fancy toys that can give us brand new molecular biomarkers for some of these traits. And the two studies down the bottom, as part of the work that principally Simone and Tim have done to try and get a better understanding of the molecular biomarkers that underpin these diseases that might be useful for management in addition to genetic improvement. So we've also done some work for genomic prediction of mainly the metabolic profiles, or that we're able to measure directly from blood samples, that includes things like calcium and magnesium that tell you about the micro mineral status, beta hydroxybutyrate and MEFA that tell you about energy balance, perhaps subclinical ketosis, urea and albumin that tell you about protein status, and albumin to globulin ratio and haptoglobulin that tell you about the immune status. So the heritability for all of these biomarkers is in the low to moderate range, and the genomic predictions are in line with what we would expect. Now, Irena, who spoke in the panel session earlier, did what I've been, I suppose, really looking forward to seeing from a scientific sense, which was to bring together the MIR data with our serum biomarkers and to see if using the MIR data can help us to lift the accuracy of those genomic predictions. Now, it's a bit, I suppose, variable by trait, but what we see is that generally speaking, the MIR data will help to lift the prediction accuracies of these traits. It's all about building bigger reference populations and combining data. So in addition to having the MIR data, having actually health and fertility records helps us to validate and improve these predictions as well. So this is absolutely taking it to the next level. So multi-omics applied to transition cow health. You probably see a bit of a theme developing here, that we're bringing together, again, a host of different information from different aspects, from cow health and fertility data to the MIR, to these molecular biomarkers and these new molecular biomarkers that we're hopefully going to find in addition to targeting specific genes. Now, all of this here is hopefully going to give us, I suppose, help us with our new or modern breeding objectives. These are pretty much common sense, that we want cows that live a long and productive life. They're efficient converters of feed into profit. They're always getting calf, very fertile. They are always very healthy. They have functional conformation, high standards of animal welfare, low emissions, and are ethically sound. And that pretty much sums up what we're trying to achieve with the next round of DairyBio. So it's sophisticated integration of state-of-the-art phenomics and genomics to help us with this vibrant dairy industry for 2030 to 2090. It's very forward-looking. And elite, resilient cows that meet the future requirements of our industry. Now, before I finish there, something that James Mann said earlier today in terms of how we can use a breeding value not just at the calf stage, but for other decisions through life. And that's actually part of our project on real-time performance prediction, that you can make the decision for a calf using just, say, pedigree and genomic data. But as an animal gets older, how do we really start to use some of the other data that we have available to make really smart decisions where the breeding value is the building block that we bring in all of those other pieces of data? Now, the challenge is absolutely how we do that in a practical sense for implementation. From a research sense, we can bring together these individual packages of data, but the real challenge lies in implementing this sort of approach. And ultimately, this will give us new ways of managing when or what time point is the optimum time point in an animal's life to cull. Should we keep her for that extra lactation, or should we make a decision to bring in an earlier replacement? And there's new generation of management tools as well, such as we were talking about earlier today with MIR. So, what we're proposing for the next DairyBio programme is these two main pillars of research projects. One that links more tightly to longer lasting cows for lifetime profitability and survival of cows and heifers, real-time performance prediction, and that transition cow genetics, and adapting to a changing environment. So next generation heat tolerance, environmental footprint, and a project that's specifically going to look at how we can use genomics to help manage diversity. So we're trying to achieve greater rates of genetic gain, but being aware of the impact of that on genetic diversity. Longer life, lower health costs, improved feed efficiency, and lower emissions. So to summarize again, two main pillars for the proposed DairyBio project, one on longer lasting cows and the other to adapting to a changing environment. And with that, I'd like to thank the funders and the staff from our Ellenbank site, in addition to our AgriBio site, and to all the farmers who have been involved in one way or another. In particular, the Ginfo farmers. We really rely on the amazing quality of data that you've been providing and continue to provide. So thank you very much for the opportunity. Graham.
Thank you, Jenny. There's a couple of things that come out of that for me. One is whoever's negotiating her contract, get it done, because with that level of enthusiasm and knowledge and development of the next generation of research people, I think we've got one of the most valuable assets in agriculture. So I think it's exciting.